Okay, so let's start. Okay, let me start so by a quick recap of what we said until now. So in the pure P spin, so we say that okay, when I do equilibrium dynamics, I have a paramagnetic phase that is ergodic above the mode coupling or dynamical temperature, and below it is not ergodic, so it's dynamically arrested. So this is equilibrium, and then if I do kind of mix the protocol where I equilibrate up to some temperature and then I switch off the temperature, so I do gradient descent and I look at the gradient descent dynamics. When I am above TD, I go to this threshold state, and so I go to the threshold state in a power law way, so the energy relaxes as T to the minus 2/3. The correlation between the initial state and the final state goes to 0, so they are orthogonal on the sphere. I have aging, and the final state is marginally stable, so it has a spectrum that touches 0. While if I start below TD, then I go exponentially to the final energy that depends on the initial temperature, and I keep a memory of the initial state, so I stay close to the initial state, and the final spectrum is gapped. I have a gap, and so it's a stable minimum. So if you can draw a kind of picture of the landscape, the energy landscape in this way. So you have the threshold energy, and so above the threshold you have saddle points, below the threshold you have minima, and so if you start at high enough energy, you end up at the threshold, while if you start at low energy, you just go to the closest minimum. Now, I just want to conclude this by giving an argument for this 2/3 that I learned from Federico. Maybe it has been done before, I don't know, but it's a very simple idea. So the idea comes from the analysis of Letizia and Jorge of the equations that show that you have this aging dynamics. So what happens when you are, so if you start at high temperature and you try to quench the system to 0 temperature, the system will start going down these saddles, then it goes to another saddle, then it goes to another saddle. But when you approach the threshold energy, the spectrum, so here you have a negative spectrum. I mean, you have negative eigenvalues in the so you have saddles, and the more you approach the threshold, and the more the spectrum becomes marginally stable, right? So this, you remember that the lambda minus, the edge of the spectrum, is linear in mu, and mu is linear in energy. So the distance of the edge of the spectrum from 0 is proportional to the energy. And so this tells you that if you are at energy E above the threshold, the number of negative directions that you have is just the integral between minus delta E, something proportional to, sorry, delta E is positive, so yes, between minus delta E and 0 of rho of lambda. So this is the area here. And since this thing is a square root of lambda minus, when you integrate, you get delta E, you get something proportional to delta E to the power 3/2. Okay? So if you are at energy delta E above the threshold, you have a number of, a fraction, let's say, of negative directions where you can lower the energy that goes like delta E to the 3/2. And so if you assume that your gradient descent dynamics is moving and it's kind of taking directions at random, the probability that you take a direction where you can go down, I mean, it's an argument, but okay, the probability that you go down is 1 over the, I mean, the probability is proportional to this, so the time is going to be the inverse of the probability to escape. And so you see that if you invert this, you get delta E going like T to the minus 3 over 2. 2 over, what am I doing? Sorry, this is 3 over 2 and this is 2 over 3. So this I think is a simple argument, but it gives you the right exponent, and so it connects the exponent of this approach to the threshold with the shape of the spectrum in the states. And it also, I think, explains nicely this idea that you go lower and lower in energy very slowly, because the more you approach the threshold, and the less negative directions to go you have. Okay, and this is what gives rise to this aging dynamics that is very interesting and is described in the work of Laetitia and Jorge. Okay, so this is the pure case. Now let's move to the mixed case, and I will follow the work of Giampaolo Folén and Federico Ricci Terzenghi and Silvio Franz. So I will take. They investigated, let's say, the simplest mixed case, which is 1/2 of 3 and 1/2 of 4. So you take the Hamiltonian of the free spin, and you. This is I think it was published in 2021, but it appeared on the archive last year, I think, in 2020. So what they did, so the Hamiltonian is essentially the Hamiltonian of the 3 plus the Hamiltonian of the 4 spin. So you have a sum of 3 spin interaction and 4 spin interaction. And the mu is -3, the energy of 3, -4, the energy, where these things are, the energy of 3 is the average of H3 divided by n, and same for E4. So now the relation between mu and the energy, and so the relation between the spectrum and the energy breaks down. If you know the energy, you don't know mu, and so you don't know the spectrum. So what they did, the first thing that they did is to compute a quantity that they call sigma of E and mu. So this is the following thing. You take a level of energy, E, and you count how many stationary points you find that have the parameter mu equal to mu, okay? And okay, it is, of course, this number is exponential, so you take the log and you divide by n, so you define an entropy. So this is 1 over n times the logarithm of the number of stationary points that have energy E, and this Lagrange multiplier mu equal to mu. So mu, remember, is -1 over n times sigma dot gradient of h, so you can compute it. Okay, and so what they find is that if you plot this for a given value of energy, so let's put here the I think they compute the annealed version, right? Federico, you can confirm. They compute the annealed. So you can question if this is the right thing to do, but I don't have time now to, so we can discuss. I don't have the answer, but okay, they compute the annealed one. So what they find is that, okay, if you plot sigma versus E for a given value of mu, it's a parabola. So you have something like this. So when the complexity is negative, it means that the number of states you have is exponentially small in n, right? Because the number of states is exponential of n sigma. So if sigma is negative, there are no states, so you stop when it becomes negative. So this is for some mu. For example, mu smaller than the threshold value. So the threshold value is defined in mu, again, as the value where the spectrum is touching 0, okay? So when mu is bigger than mu threshold, you have gapped states. And when mu is smaller than the threshold, you have unstable states. So if you take, for example, some stable value, you get something like this. And then you can do it for unstable values, and you get another parabola like this. So this is unstable. And if you do it for the marginally stable value, Then you get another parabola. Let me maybe change color. You get some other parabola like this. This is difficult. Okay, so this is the marginally stable states. And then what you can do, you say, okay, but then for a given energy, if I fix an energy, then I have states with different mu, but they are exponentially different in number, right? Because at a given mu, I have exponential, I mean, the number of states is exponential of n sigma of E and mu. So the states that dominate at a given energy, the most numerous ones, are the states that maximize this quantity. So what you have to do, you take a kind of the envelope of these parabolas that shift with mu. So you have an envelope here that defines this a function sigma of E. So this is the maximum over mu of sigma of E and mu. So at each level of energy, the dominant states have the mu that corresponds to the parabola that is tangent to this curve. So this value here, it's kind of the threshold value. So it's the energy at which the dominant states are marginally stable. Above this energy, most of the states are unstable. Below this energy, most of the states are stable. But now, unlike in the pure case, you still have all kind of states, because you see that at the given energy, you have you have many parabolas that are there, okay? I mean, of course, also in the pure case, you have at finite n, there can be saddles here, but they are not, I mean, the probability that you have a finite fraction of negative eigenvalues here is really small. It's much smaller than e to the minus n. Okay, while in this case, with probability e to the minus n, you can still have a finite fraction of unstable states. So this seems to make a difference. It's not completely understood, I think, but I mean, clearly there is something different in the landscape. And so then what they did was to do the same study as there. So you start, so okay, the equilibrium phase diagram is exactly the same for the mixed p-spin. So you have a Kautzmann temperature, and you have a dynamical, you have an MCT, or dynamical temperature. And so then what they did in this work was to start in equilibrium at temperature T, and do the gradient, solve the equations, these dynamical mean field equations for the gradient descent, and see what happens. And what they find is that there is, so if you start at high temperature, so here you have the threshold. The threshold is defined in that way. Here you have the ground state. So if you start at high temperature, then you end up in the threshold, and everything goes like in the pure case. So you lose, oops, this should be straight. You lose memory of the initial condition, and you go to the threshold as t to the minus 2/3, and you have the same kind of aging, and everything is the same. If you start at very low temperature, also you get the same situation. So you go to some value of energy that depends on the initial temperature, and you go exponentially fast. So the gradient converges, the gradient descent converges exponentially fast, and you keep memory of the initial state. So you have many, I mean, you go to a given energy, but you have many possible states at that energy, depending on the initial state. The difference is that these two things do not match at TD, like in the other case. So here, they define a temperature that they call T onset. And so now this let's say, memoryless aging regime only happens for T bigger than T onset, and this memorious regime at low temperature only happens below some temperature that they call TSF, which stands for state following. So the name comes from the fact that, as I told you before, you can compute the final energy and you can compute the overlap between the initial and final states of the gradient descent by using this Franz-Parisi potential, which is also called state following, and it, I mean, so it is a way to compute the final state without solving explicitly the dynamics, so it leads you to simpler equations that you can solve more easily, let's say, than the dynamical ones. So that, I mean, that's the origin of the name. So essentially the idea is that when you are in this regime, you cool it, I mean, you start in equilibrium and you quench your system to zero, you are essentially following the evolution of this initial state in a kind of adiabatic way down to zero. So if you, instead of doing an instantaneous quench, you do it, you cool at a certain speed, you will follow essentially the same curve. That's why it's called state following, okay? You can always follow these states adiabatically. Okay, and then what happens in between? So there is this gap between the state following and the onset temperatures, and what they find in that case is some kind of intermediate phase where there is so if you start at some point in between, you go to a final state that depends on the initial one. So the energy of the gradient descent goes to a final value that depends on t, on the initial t, but it's not exponential, it's again power law with an exponent that looks like is the same as the 2/3 that you get above, and the correlation between the initial and final state doesn't go to zero, it goes to some finite value, but the final state is marginal. So what happens in this regime, in this intermediate regime, is that you have memorious dynamics, so you keep memory of the initial condition, you don't go very far away, so you have your sphere, again, you are starting in equilibrium at some state sigma 0, you move a little bit, not very far, but you still find one of these rare marginal states that are present below the threshold. So you go below the threshold, and so you are not going to the typical states that are there, because the typical states, the typical stationary points of the energy that are below the threshold are minima. They are minima with the gapped spectrum. So what seems to be the happening is that the gradient descent is starting from some kind of state that is unstable and is stopping on a marginally stable state. So when the spectrum touches zero, you stop. So again, you have this argument that gives you the 2/3 exponent that tells you that you are moving down in energy, and every time you move down, you have less and less negative directions, and you stop when you don't have the negative directions at all. But so what is interesting is that this happens below the threshold, and at some point there is some temperature below which you don't have this anymore, because you could say, okay, but maybe I always have this. This looks natural, like you start in a stable state and you stop when you become marginal, but it's not always the case. At very low temperature, you start in a stable state, but still you end up in a stable state. Okay. So you can have all free behavior, all yes. No, I don't think so, right? The state following temperature is not the temperature at which you end on this point. It's above. No, no. There is really something in the structure of this landscape that defines this free regime. So, okay, so I think this is I mean, it's a new finding, and I mean, it leads to a certain number of open questions that are related to exactly what defines this. Yeah, I think they tried many others, and it seems to be. Yes, yes. It should be. I mean, the equilibrium should be in the one RSB class, let's say. I think for any infinitesimal thing, really need to. Yes, yes. So it seems to be the generic behavior, at least for systems that are in the one RSB class, let's say. And so the last thing I wanted to show on this is that, so if you plot now the energy of the final state as a function of the temperature of the initial state, which is a plot that is often done in the literature on glasses, what you find is something like this. So up to, I mean, down to the onset temperature, you are on the threshold. So you get the energy is independent of the temperature, on the initial temperature. Then you have this intermediate regime where the energy goes down, so you go below the threshold, but you still reach marginal states. And then below the state following temperature, you still go down, but now you reach stable states. So the gradient brings you to stable states. And this is something that has been done in structural glasses, in three-dimensional models of particle systems, and it looks similar, except that this transition between, I mean, it seems to be power law at all temperatures actually. So Ludovic, I don't know if Ludovic is going to talk about it, but maybe Ludovic is not there. But anyway, maybe he will talk about it. But he has a nice paper, recent paper on this, where he shows that it's always power law, and it's probably due to the fact that in three-dimensional system you have localized modes, and so it leads to new physics, let's say. Okay, so that's the end of the first part. So what I wanted to, I mean, just to summarize, so I think this is a kind of generic picture. I mean, this one, the one of the mixed case, is a kind of generic picture for rough landscapes of glassy systems, at least at the mean field level. It's possible that in 3D, perhaps this transition does not exist, and the physics might be different because of localized modes. You can get all this, as I told you, from relatively simple analytical solutions that you can construct using either replica methods or dynamical mean field theory. You have rigorous proofs in some cases, and well, and so you have these three regimes. So I described, I told you I described a kind of simple version of simulated annealing, where you anneal up to some temperature in equilibrium, and from there you go very fast. Of course, you can consider different protocols where you cool at a certain rate, or where you have a time-dependent rate, and then you can have, or maybe you can also consider cycles when you cool and heat up the system, and you can do training and things like that, and you have a very rich phenomenology that is associated to all these transitions and things like that. You can also add, I know that there are people interested in active matter in this school, so you can add terms to the dynamics that look like what you do in active matter, so persistent noise and things like that. and this is work by Ludovic and Jorge Kurchan, and so you have also an interesting phenomenology associated to the how the active terms allow you to explore this landscape. Okay, now the second part that I will describe maybe a little bit faster is that there is one thing that is missing. So there are many, let's say, these models have become these mixed p-spins, the pure spin first, but then the pure p-spin, but maybe now the mixed one, have become the kind of simplest toy model of Glassy system for the reasons I just mentioned. But there is one thing that is missing, and this is jamming. So these models do not have a jamming transition because there is no, I will explain it in a second. So you should think of these models like models for glasses in the high density regime, where particles are interacting all the time. So in order to extend this phenomenology to include jamming, you have to consider a slightly more complicated class of models, and these are constraint satisfaction problems. And I would say that the toy model in this class, the analog of the p-spin in this class, is the perceptron. So that's the second toy model I want to introduce. So the perceptron, again, we have a spherical spin. So we are on the same space, a sphere of size n. But now the Hamiltonian is different. The Hamiltonian is the sum over m from 1 to m of some potential that depends on a variable h. And the variable h is the scalar product of some vector xi with the vector sigma divided by square root of n for to make it of order 1 minus a constant k. So what is the meaning of this? So the idea is you have a sphere, you have your you can think to this as a particle sigma on the sphere, and there are obstacles. So xi, one of these vectors xi is an obstacle, and so the scalar product, so this variable h is essentially the scalar product of xi and sigma minus some constant, and here you have a potential. So this is related to the distance, if you want, between sigma and xi. And here you have a potential, and this potential is 0 if h is positive, because this is the Heaviside theta function, and it's h squared if h is negative. So this is a kind of cost function or loss function, depending how you want to interpret the problem, that is giving a penalty to negative h. So if the two vectors are, if sigma is too close to xi, then you pay a price, the opposite. I mean, okay. Of course, I mean, you have minus xi, so if you want to think to it as an obstacle, so you want sigma to be close to xi, which means you want sigma to be far away from minus xi, so the obstacle is minus xi. Anyway, so this is the particle, let's say, interpretation, but this problem actually comes from, let's say, machine learning, and it's probably it's the simplest, I mean, one of the simplest classifiers that you can imagine. So let me just try to motivate it from a machine learning perspective. So the idea is you have some input, so you have some input x1, xn, which is a vector, and you have an output y, okay? And you have, so what you have is a set of examples of X, so you can think to X as your image, and to Y as your label of the image, which is dog or cat, as usual, and you want to decide, given X, you want to decide if the image is a dog or a cat. So you will have two values of Y. And so you want to fit, you have this unknown function that for a given input tells you dog or cat, and you want to try to fit, to learn this function. So the simplest fit is, so it's linear, it's a linear fit, plus the simplest nonlinearity, you take the sign. So you take the scalar product of your image with this vector sigma of weights, and then you take the sign of this, and if it's positive, you decide it's a dog, and if it's negative, you decide it's a cat. Now, so if you are given m examples of images that you know that are dog or cats, then you have some pairs x m y m for m going to 1 to m, and you would like, from this training set, you would like to learn the sigma. So what can you do? So you want to solve in such a way that ym is equal to the sign of sigma dot x for all m, right? So if you multiply, but y is plus or minus 1, so if you multiply on both sides by y, you get that 1 should be y times this sign, and this is equivalent to say that y times sigma dot x should be positive, right? So what you get, if you call now psi m equal to ym xm, this amounts to impose that sigma dot psi should be positive for all m. And so you see that this is a special case of this problem where when this constant k is equal to 0, you are trying to impose, when you minimize the energy, if you are able to minimize the energy and you get 0 energy, so if then it means that all these h are positive, and so it means that all these scalar products are positive, and this is what you want, okay? So the xi here, the xi are called patterns, and they depend on this training set that you have. Now, so you can think to this perceptron as a particle problem where you have a particle moving on a sphere with obstacles. You can think to it as a classifier where you have data and you want to decide if they are cats or dogs or whatever, and you can also think to it as a constraint satisfaction problem, in the sense that you have a set of variables, sigma, and you want to find a state of this variable sigma that satisfies these constraints, that the h should be positive. And so in this sense, it's kind of similar to the problem of packing spheres, in which you have particles x in points x, and what you want to do is to solve, to find the configuration of the particles such that the gap between pairs of particles, let's say that the size of the particles is 1, is positive. So I mean, this is more than an analogy when you start to write equations for the perceptron, and when you start to write equations for spheres in the limit when the dimension of space goes to infinity, you basically find the same equations, up to some little technical differences. Now there should be someone else laughing in the room, but where is Alessandro? I don't see Alessandro. Okay. Anyway, little technical difference, but okay, that can make your life difficult, but okay. So you see, okay, it's a quite general problem. So now the difference, now I will forget about sphere packings, and what I want to highlight is the difference between this and the p-spin. So in the p-spin, the energy landscape, I mean, you have all these interactions, and the minima, I mean, the stationary points, the points where the gradient of the Hamiltonian is 0 are always isolated, essentially. You always have isolated minima or saddle points. Here, the situation is very different because you can have what I will call lakes. So if you plot the energy as a function of sigma, you can have a situation, because now the energy has this theta function that makes it so the contribution of one of these obstacles is going to be 0 whenever it is satisfied, whenever this constraint that this variable is positive is satisfied. So, and it will stay 0. So if you manage to find a point where all the constraints are satisfied, and you perturb it a little bit, maybe they will stay satisfied. This depends. But if you think about packing spheres, if the density is very low, all the spheres are far away. So if you move them a little bit, they will not overlap. So you have that the energy is 0 and it will stay 0. So you can have a lake, and then you can have the mountains next to the lake. So this is, so the lake is going to be a region where the energy is totally flat, totally equal to 0. So now, now this can include jamming, because jamming is essentially the point where lakes become points. And that's what I want to try to describe in the next half an hour. Okay. Okay, so the last thing before I enter into the discussion of the dynamics is that also in this model, so if we take the perceptron, okay, sorry, one more thing is that I will take now I will focus on the case where the patterns psi m are completely random. So I will take the components of these vectors to be Gaussian, independent, with 0 mean and unit variance, because this is a tractable case. Of course, in this case, there is nothing to learn because the training set is totally random. So it's a kind of a null model for learning, if you want. But okay, so of course, I mean, there is no relation because the psi are totally random. There is no relation between the input and the output. So we are going to forget a little bit about classification and just think to it as a problem of obstacles or satisfying constraints. So what you can do next in this problem is to compute, to do the same thing that we did before. So classify the stationary points. So I can compute the Hessian. So the second derivative of H, and then I should always add this spherical term because the variable sigma is defined on a sphere. So if you do that, you see that the energy is quadratic in H. So every time you take a derivative, you remove an H. So in the end, what you get is 1 over n sum over m psi m I psi m j times theta of minus hm plus this diagonal shift. So again, and okay, again you have mu. As in the previous case, mu is equal to minus 1 over n sigma dot the gradient. And when you compute this, you get alpha. So alpha is going to be the ratio of the number of constraints divided by the number of degrees of freedom times the average of H squared plus the average of H. And this average I'm going to define as 1 over m sum over m of f of h m theta of minus hm. So what you have to do, so to compute the Hessian, what you have to do, you have to take only the constraints that are unsatisfied, so the variables h that are negative. You take them, and for those, you do essentially an external product of the vectors psi, and you sum over all this. Because of course, the variables that are satisfied, the energy is 0, so they do not contribute to the derivatives. And okay, to compute mu, what you have to do is to take the average of h squared plus, there is a kappa missing. You have to take the average of h squared and of h, but only over the unsatisfied constraints. So if you want, over the overlapping particles. So now, I told you in the p-spin the matrix, the Hessian matrix was a GOE. So here it's a Wishart matrix, which is also a well-known set of random matrices. But this is true. I mean, again, in principle, these things depends on this psi. The psi are the quenched variables in the problem, so they are given to define the problem. And the h are the dynamical variables. They depend on the sigma. And in principle, in the final state of, if you want to analyze gradient descent, in the final state of the gradient descent, the h and the psi are going to be correlated because the h depend on the psi. You fix the psi and you try to minimize your energy. But it turns out that in the limit of n going to infinity, you can, I mean, you have to send n to infinity and m to infinity at fixed ratio. And then you can neglect this correlation. So this becomes a random matrix of the Wishart type. So it has Marchenko-Pastur spectrum. So like in the p-spin, you can compute exactly the spectrum, and it is equal to the following thing. I will write it in this way, like I1 minus c plus times delta of lambda plus mu plus 1 over 2 pi square root lambda minus lambda plus minus lambda divided by lambda plus mu. This is only true for lambda minus. I mean, this term is defined in between. So this means 1 minus c if this is positive and 0 otherwise. And lambda plus minus are given by square root of c plus minus 1 square minus mu, and c is given by alpha times the average of 1. So the average of 1 defined in this way. So this is just 1 over n times the sum over m of theta of minus hm. So what does this mean? So the first thing is that you see that, like in the p-spin, the spectrum here depends only on two parameters that are macroscopic, okay? It depends on mu and c. And mu and c are intensive quantities that are averaged over the full system. So it doesn't depend on the details of the point where you are. Now, mu is some average of the gaps, the h. And c, that is a very important parameter, is what? Is here you have to sum. This quantity here is the sum of 1 every time that there is a negative h. So this is the sum of all the constraints that are non satisfied. And then it's divided by n, not by m, because I mean here it's defined with an m, but you multiply by alpha. So it's alpha is m over n, so you get 1 over n. So this is the ratio of the number of constraints that are unsatisfied divided by the number of degrees of freedom. So if you want, in the language of particles, is the kind of the number of contacts divided by the number of degrees of freedom. So this is what is called in the jamming literature the isostaticity index. Staticity index. So in the case of, for those who are doing jamming, this would be Z, the contact number, divided by 2D, the dimension of space. So when it's 1, you have the same number of degrees of freedom and of unsatisfied constraints, so of overlaps. So 1 is a special value of this this thing. No, because there are even away from the lakes, there can be some constraints that are satisfied and others that are not. Good question. You should prove it. I mean, no, I don't know. I mean, you can make the assumption that that you can. It doesn't disappear. Because when you, I mean, this number here is exactly the number of contributing terms, so it doesn't disappear. But you essentially you bring this out of the sum. You say, okay, I have the patterns that I select. So let's say in a given state, some patterns are on and others are off. Those that are off have 0 are here and the others are here. And what I'm saying is that the patterns that are chosen to be active are uncorrelated. I'm taking the xi randomly. So it's the correlation property, and I'm not able to prove it. But I mean, if you do numerics, it clearly works. Yes, for stationary points of the Hamiltonian. Okay, so now that we have the spectrum, we can classify the kind of situations that we can have. And so what I would like to say is that, okay, this model can be solved as the p-spin with the same techniques, but it's more difficult, because in the p-spin you can obtain the closed, let's say, closed equations for all the correlations and so on. And here you get, again, closed equations, but some terms that appear in these equations are not explicit. They have to be computed as averages over some stochastic process. So when you try to solve the equations, you have to numerically solve this stochastic process, and it's difficult. So if you want details, Alessandro Manacorda is working on that and struggling with that a lot. So we can tell you more if you want. So the replica calculation for these models have been done. They are doable. A bit more involved than the p-spin, but doable. The complexity calculation, I think, has not yet been done. You can correct me if I'm wrong, but and the dynamical mean field equations are we are trying to solve them. We have the equations, but we are not really able to solve them. So what I will describe is more like from now on. What I will describe is more like the result of numerical simulations of the model. Yes. Well, in the real classification problem, they're probably not even IID. They might be correlated. If it's an image, one pixel and the next pixel are probably correlated. So, yeah, this is really a toy model. So I'm not going to. Yes, I'm taking it as a. Yes. So there is some work on in that direction. There is, I think, a paper by Kabashima and other people where they do a correlated version of the xi. So yes, probably it can be extended to that case, at least if the correlation is not too difficult to. Okay, so what kind of So I told you this is the spectrum, but let me give you now some examples. So let me try to classify the kind of states that we can get. So the first type of states that we can get are when c is smaller than 1 and mu is negative. So I need mu to be negative because you see if c is smaller than 1, then this term here is non-zero. So I have a delta peak in lambda equal to minus mu. And so if mu is positive, then I get an unstable state. Now I want to classify the minima, the stable states. So I need mu to be negative. And now you see, if I want mu to be negative, if you look to the formula for mu, this term is surely positive, and this term is surely negative, because h, this average, is only over negative gaps. So I need k to be positive. If k is negative, it's impossible, because mu is for sure is positive. Okay? So these states, now k is a parameter of the model, and I will tell you that, I will show you that k positive or negative is very different. So, but these are only possible for k positive. And then, in this case, what you get is a delta peak. So your problem is hypostatic, so there are less constraints active than degrees of freedom. So you have a lot of not zero modes, because in this case, I mean, if mu is negative, then you get a delta peak, but because mu is just a shift, so essentially these are zero modes for the rest of the matrix. So you get a delta mu, and then you get something that looks like semicircle. It's not exactly a semicircle, it's a Marchenko-Pastur, but it's something like this between lambda minus and lambda plus. Okay, so this is a minimum, but because the number of patterns here is smaller than the number of degrees of freedom, this term of the matrix has a lot of zero modes that are shifted by mu, and they appear in this way. So this is the first possibility. The second possibility, well, is the, okay, let's group them together. If mu is equal to 0, then this is slightly shifted, and this term becomes really zero modes. And lambda minus, you see, lambda minus is square root of c, I mean, let's write it here. This is square root of c minus 1 square minus mu, plus mu, y minus. Yes, minus. Yes, so if mu is 0, but c is smaller than 1, then this is positive, right? So you have this delta can go to 0, so you have a finite density of zero modes, and then you have a gap, and then you have the rest. So these are hypostatic minima. Then you can have the isostatic case when c is equal to 1. And in that case, there are two possibilities. Either mu is equal to 0. So if c equal to 1, then you don't have this delta, because now the number of degrees of freedom is equal to the number of states, so you don't have zero modes here. You have only this. And if mu is 0 and c is equal to 1, then lambda minus is equal to 0. So it's marginally stable. So lambda minus is equal to 0, and however, you should note that there is a lambda here in the denominator. So if mu is equal to 0 and lambda minus is equal to 0, here you have square root of lambda divided by lambda. So you have 1 over square root of lambda. So the spectrum is divergent here. It's something like this. So here you have rho of lambda is going like 1 over square root of lambda, which for those who are more used to frequencies gives you a flat density of states. So the density of states in frequency is independent of frequency, and it goes to a constant at zero frequency. So these are, let's say, isostatic states. And they are marginally stable, and because, I mean, the spectrum is touching 0. These are hypostatic, and then you can have also hyperstatic states with c. I forgot to, I mean, there is of course the case where c equal 1 and mu is positive. This is possible in principle, but in practice it doesn't seem to happen in the model. So it seems that when you have c equal 1, typically mu is equal to 0. So otherwise what happens is that you just shift everything by mu. Okay, so if c is bigger than 1, then in order to be stable, now you don't have this term. So in order to be stable, what you want to have is only this one. I mean, you want lambda minus to be positive. So so the equation becomes, the stability condition becomes this one. And then you have a spectrum like this, with lambda minus and lambda plus, and here is square root of lambda minus lambda minus, so it's like in the p-spin. And if lambda minus goes to 0, then you're back to this case. And an interesting remark is that if you linearize this when c is close to 1, then you introduce delta c equal to c minus 1, so the deviation from isostaticity. What you get is this condition becomes delta c, so this is going to be linear, this is going to be quadratic in delta c, so you get delta c square bigger or equal than mu, and mu, when you go close to the, when mu is close to 0, means that the gap are all close to 0, so this term is much smaller than, this term is negligible with respect to this one. So mu is essentially, is linear in H, and in the particle language, H is the gap, so the average of H is the pressure. So what you get is the relation that in order to be stable, delta C should be bigger than the square root of the pressure. And this is a relation that has been derived by Mathieu Viard and collaborators in other ways. So it's interesting that you find it back in this case. And then in this case, well, you get a square root spectrum close to the edge. Okay, so these are the three kind of minima that you can have. Yes. M. This is M. But so then when you, but then C is equal to alpha times the bracket. Yes, sorry, it's I've never found a really good notation for this. Okay, so these are the type of minima that you can have. Now let's see what happens when we try to study the landscape. How are these minima organized in the landscape? Yes. Yes. Yes, it will. So yes, good point. So this is the bulk of the spectrum. There can be eigenvalues that have a weight 1 over n. So there is only one eigenvalue, and so when you take the thermodynamic limit and you look at the spectrum, you don't see them, but they will play a role in a second. So okay, so what I want to do to conclude, so in less than 15 minutes, is to give you an overview, very quick overview of what happens now in a special case, which is the simplest case where we start from infinite temperature, and then we go to T, and then we switch T equals 0 instantaneously, so we do gradient descent. So now I will restrict to gradient descent starting from totally random state, and of course then it could be generalized to finite initial temperature, but this has not been done, so I don't have results. So before I do that, I will show you again quickly the phase diagram of the equilibrium calculation. So I can do an equilibrium calculation. So if let's say if the gradient descent were able to equilibrate down to 0, then what would I see? And this you can do, this calculation can be done with replicas. And sorry, I misplaced the axis. So you can compute what would be the final state if the gradient descent would be able to, were able to stay in equilibrium at all times. And it looks like this. You have many lines. So the two control parameters are alpha. The alpha is the density of constraints that you have to solve, and kappa is this parameter that was appearing in the constraints. So the constraint M is the scalar product minus kappa. I forgot to tell you that in the classification problem with kappa positive, so if kappa is positive, then it becomes a kind of, of course, I mean, it's more difficult if the more you increase kappa, the more the problem is difficult, because you want to constrain more and more the sigma. And you can show, so kappa equal to 0 was the simple classification problem I discussed. So if kappa is positive, it amounts to a stricter requirement where you want to classify some data, and also you want the classification to be robust to a little bit of noise. So if you add a little bit of noise into the data and you have a finite kappa, then you keep classifying them correctly, okay? So that's the original motivation for why this kappa has been introduced. So you see that you have, first of all, you have two lines. You have one line that separates a phase where there is no solution to the problem from a phase where there are solutions. So this is called the SAT and SAT transition, or jamming transition in the case of particles. So this is so below this line, you can find the configuration of the sigma such that all the H are positive, while above you cannot. Okay, but then you have other lines. So one line, which is like this, and then you have other lines like this, and like this. So I will not describe all of them, but what I want to say, I mean, the important point is that these lines separate a region. So outside of this red line, then the problem is kind of paramagnetic. So you have a unique, I mean, you have the solution, you have a lake. For example, in the SAT phase, you have a lake. So if you plot the Hamiltonian versus sigma, you have a lake. And your lake is essentially a single connected component, okay? While above this red line, the lake breaks into many lakes. There are many lakes and they are essentially disconnected, okay? So here it's still SAT, here it's unsat, above the violet line, and here it's still SAT. So there are lakes, but the lakes are disconnected. And okay, here the transition from connected to disconnected is continuous when it's red, and here when it's green and so on, it's a transition, it's a discontinuous transition like in the p-spin. So, but I don't want to enter too much into these details. I'm happy to explain you if you want to know the details. But now, so let's go back. So this is what would happen if the problem was, if the gradient descent was able to reach the equilibrium. What happens in reality? There are several cases. So the first case, let's start from the simplest case, which is here. I will call this the unsat convex case. So if when you do the replica calculations and you try to compute the ground state, so here the ground state is at positive energy because you are not able to satisfy all the constraints. So here the energy is 0, here the energy is non-zero. And what the replica calculation tells you is that you have a unique minimum. You have a unique minimum, and this minimum when you compute the spectrum from the Marchenko-Pastur is like this. No, sorry, is like this. So it is a stable minimum with a gap. It's hypostatic, so you get C smaller than 1. And you get, and mu is positive because you have, you are in the unsat phase, and you remember mu was equal to alpha h square plus kh. So both these terms are non-zero, and mu is non-zero. So your spectrum is like this. You have a gap, and when you do gradient descent, what you expect is that you converge. So the energy minus the energy of the minimum, which is the unique ground state, is going to be exponential of minus t over tau, and tau is related to this mu, is the minimum eigenvalue. So you can compute, so in this phase here, you can compute all these things from the replica method, but you can also not solve, but you can show from the dynamical equations that you recover the replica solution. This was done by Francesco Urbani. Well, so this is the simplest case. You have unique minimum, harmonic, gapped, everything is simple, and you just, if you start from initial configuration, you just go to the minimum, and that's it. And you can write your code and do that. You can check, it's very easy. Yes. Minus, yes. Because mu is negative. Oh, sorry. Thanks. Mu is negative. Sorry. Then, yes, in all this region here, let's say. So for all positive k and alpha above the jamming or sat-unsat transition, it's like that. So these are results, by the way, these results are from Elizabeth Gardner and Bernard Derrida in the late 80s. Not exactly in the same version, but more or less in the same version. Then, okay, the second case, which is what happens here, is, so in the convex, let's say, SAT case, is that you have one lake, and that's it. So you have one lake, you have this is the lake. So this is the space of solutions. And now, so what happens, and this you can you can find this from the replica calculation. And so now if you do gradient descent, what do you expect? That you start from very high energy, you follow you go down the mountain, and you end up on the shore of the lake. On the other hand, if you look, could be, but it is not. No, I agree, but in this case it happens to be, yes, but in this case, in this region, it doesn't happen. In this model, in this region, it will happen in the other region, but here it doesn't. So you just go down, you get to the lake, and but if instead of doing gradient descent, you put a little bit of temperature, so you do some thermal protocol and you cool the system, then the thermal noise will allow you to diffuse into the lake. So when you switch off the noise, you will be in the middle of the lake. So this means that you have a different phenomenology if you look. So if you plot, for example, suppose you take a line here at fixed k, and you plot the final number of contacts that you have. So if you're doing a thermal protocol, it will be something like this. So it will jump when you cross this line at the jamming point. If you do gradient descent, instead it will do something like this. So above it's the same because you have a unique minimum that is harmonic. So whatever you do, you end up here. But below, when you have the lake, if you do thermal, you end up with 0 contacts because you're in the middle of the lake and all the H are strictly positive. While if you do gradient descent, you end on the shore, and on the shore, some H are equal to 0. They are marginally satisfied. So you get a non-zero. And this value here, I told you, is smaller than 1, is below 1. Okay, so you have a sat-and-sat transition. And the spectrum of the final state, if you do gradient descent, is like this one again, but with mu equal to 0. So you have a delta peak here. You have a delta peak, and then a gap, and the modes. So the important point is that you see, in this case, for positive k, you have a transition between the SAT phase where you find solutions and you have this lake. At the jamming point, the lake closes and becomes a point. Then it goes up in energy, so it's not a solution anymore. And but all this happens in a simple way where there is just this lake, and the gradient descent will always go to the right state at 0 temperature. The thing that is interesting, however, is that the relaxation time of the gradient descent, so if you plot on the same line the relaxation time, what you find is that it diverges at the jamming point. And this is something that is also known in many constraint satisfaction problems, like in KSAT and so on, that when you are close to the transition from solution to no solution, the time it takes to find solution diverges. And you can show numerically, so all this is numerical work done in this case by Sungmin Wang and Harukuni Keda. I will send you a reference. They show that this diverges, and the divergence is controlled precisely by an isolated mode that is not described by this bulk of the spectrum. And so you can check their paper if you want the details. Okay, the very last thing I will say is what happens in the non-convex case, on the other side, when kappa is negative. So what happens there is that now you don't, now what Gerard was saying happens, so you don't relax to the lake anymore. I mean, let me modify the plots. I will do it very, very quickly, and then I'm happy to discuss it during the rest of the school if you want. The main difference essentially is that if you do thermal in equilibrium, you get something like this. And if you do gradient descent, so now I'm doing on a line here, I'm going up. I increase the difficulty of the problem, I increase alpha. So if I'm in equilibrium, I go to this point, and then I have a jump. But if I do gradient descent, I will reach 1. Now the jamming is always isostatic, so I always have 1 at the jamming point, and I get something like this. So now the gradient descent will stop finding solutions before. So when there are solutions, there is a region where there are solutions to the problem, but when I do gradient descent, I cannot find them. I get stuck on local minima, and this happens, and this transition from solution to no solution happens always at c equal 1 when the system is isostatic, and this gives rise to particular critical properties that you can study from the replica method, and for the moment not from the dynamics, unfortunately. But essentially, so what happens is that here, in this phase here, so above jamming, you recover the p-spin phenomenology, so you still have a threshold, and you still go like t to the minus 2/3 to the threshold, because the spectrum is like this. While below, here, you go exponentially to the shore of the lake, that at some point disappears, and when it disappears, you have a spectrum like this, so you have a flat. So you have exactly the same phenomenology that you have in the jamming of spheres, if you know about it. And you have also divergence. So now the relaxation time is infinite. And I'm done. The relaxation time is infinite on the jammed side because it's power law. It's always marginal, while it is finite and diverges at the jamming point when you approach it from below. Okay, sorry, I went a bit fast on this last part, but I will send you the notes, and I'm happy to discuss. I'm staying until the end of the school, so I'm here available whenever you want to discuss. So the last, the conclusion of this is that the perceptron is another toy model, very simple, but still it has a very rich phenomenology. You recover the p-spin in this corner, and then you can extend the p-spin phenomenology to this complete phase diagram with in particular, the jamming transition and the jammed phase, and you have the same dynamics of jamming in particles. I think maybe Ludovic will talk a little bit about it. Unfortunately, it's harder to solve than the p-spin, so while we understand the equilibrium curves, so all this blue we can compute, we are not able for the moment to solve the dynamics analytically, so we only have insight from numerics. We have some results from the dynamics, but not a complete solution. That's it. Thank you.